Hi everyone, I hope you're doing well. In this lecture, I'm going to take you through the process of drawing the shear force, bending moment, and axial diagram for this frame shown in this figure. In this frame, we have member BC, which is subjected to 2-point loads, 20 kN each, and we have member AB, which is subjected to a UDL of 5 kN per meter intensity. And this UDL is acting along the vertical projection of this member AB, and this here is the horizontal projection, and it has no load acting upon it. This sort of loading, which acts along the vertical projection of an inclined member, represents wind loading. To draw shear force, bending moment, and axial diagram, we will use these steps here. First, we will determine support reactions or external reactions. At A point, we will have two reactions since there is a hinge. This reaction would be RAY, and this reaction, horizontal reaction, would be RAX. And at C, since we have a roller, we only have one vertical reaction, that is RCY. And after determining support reactions, we will draw the free body diagram of this frame and separate these members, apply reactions here, and try to determine end member forces or member forces at joint B. After the second step, we will write shear force and moment equation for these frames, and in the end, we will utilize those equations to plot the shear force, bending moment, and axial diagram. So let's get started. To determine support reactions, we will obviously apply condition of equilibrium, that is summation of f of x, summation of f of y, and summing the moment about a particular point. So first, let's apply summation of f of x, summing the force in x direction. Let's assume that this is x direction and this is y direction, and take a rightward force as positive. So we have RAX going towards the left, it's going to be negative, and we have the resultant load due to this UDL acting here at a distance of 1.5 meter from the bottom. And the magnitude of this resultant is going to be equal to 5 into 3, which is the area of this UDL, and it's equal to 15 kN. So 15 kN is going towards the right, hence positive. RAX from here is equal to 15 kN. Now applying summation of f of y equals to 0 and taking upward force as positive. RAY and RCY are acting upward, hence positive, and these two 20 kN force are acting downward, hence negative. So this is equation number 1. Now applying summation of moment about A point equals 0 and taking clockwise moment as positive. So first of all, we have this 15 kN force with a perpendicular arm of 1.5 kN, and we have this 20 kN force creating clockwise moment about A point, and it has a perpendicular arm of 5 meter. 1 plus 4, 5, so 20 into 5. And this 20 kN force has a perpendicular arm of 6 meter. 1 plus 1, 2, plus 4, 6. And in the last, we have RCY creating counterclockwise moment, hence negative, and has a perpendicular arm of 4 plus 3, 7. And if we solve this equation for RCY is equal to, and now substitute this value of RCY in equation number 1. Equation number 1 implies that .357. Now let's draw the free body diagram of this frame. First, apply support reactions at A point, at C point. And apply the resultant load of this UDL And now we need to figure out a way to calculate internal forces or member end forces at this point, and then transfer these forces towards here. And this would give us the complete free body diagram for this frame. So let's name the vertical force acting here as RBAY, and this force as RBAX, and the moment acting here, that's represented by MBA. And to determine these forces and moment at B point, we will apply condition of equilibrium to this whole member AB. And it's entirely up to you whichever direction you choose for these forces and this moment. In the start, your answer after applying condition of equilibrium will tell you whether you have assumed the correct direction or not. If it's positive, then you assume the right direction. If it's negative, then you need to change the direction of that force. That's it. Alright, so first determining RBAX by applying summation of f of x, taking rightward force as positive. We have this 15 kN force going towards the left, negative, and we have this 15 kN force going towards the right, hence positive. RBAX is assumed to be going towards left. And if you calculate RBAX from here, is equal to RBAX is equal to 0. And now let's try to calculate RBAY by applying summation of f of y equals to 0. Taking upward force as positive, we have this RBAY and 5.357 acting upward, hence both positive. And do we have any other force? No. RBAY from here is equal to minus 5.357. And the negative sign here indicates that the assumed direction of RBAY is incorrect. It should be going down. To evaluate the value of MBA, we will sum the moment about A point and equate it to 0. So summation of moment about A point is equal to 0, taking clockwise moment as positive. So we have this 15 kN force creating clockwise moment, and it has a perpendicular arm of 1.5 meter with respect to A. And secondly, we have this 5.357 force creating a clockwise moment about A point with a perpendicular arm of 4 meter. So 5.357 into 4. And we have this moment acting in counterclockwise direction, hence negative. And if we solve this, MBA from here is equal to 43.928 kilonewton dash meter. Alright, now to transfer these internal forces from this end of the member to this end of member BC, we just need to apply them in reverse sense in order to maintain equilibrium at this whole joint. And here we can see that RBAY is going downward, but at this end it will be shown as going upward. And since RBAX is 0, we don't need to apply it. MBA is acting here in counterclockwise direction. Here it would be in clockwise direction, and it's equal to 43.928. Now the last thing that you can do here is to check your calculation, and you can do that by applying conditions of equilibrium to this whole member BC. So let's check summation of f of y whether it's equal to 0 or not. So summation of f of y equals 0. I'm going to take upward force as positive. So we have 5.357 and 34.643 going upward, hence positive. And 220 kilonewton loads going downward. And this tells you that member BC is in equilibrium and your calculations are correct regarding the vertical forces. And you can check, similarly you can check summation of f of x and summation of moment about a particular point, and this would also equate to 0. If it's equal to 0, it means that your calculation regarding horizontal force and the moment is also correct. If it's not, you need to check your calculations here. Now I'll draw the shear force, bending moment and axial diagram for member AB. But in this sort of problem, we need to convert the forces, internal forces or support reactions into components which are parallel and perpendicular to this member AB. For instance, if I take this force, I need to calculate component which is perpendicular to member AB and a component which is parallel to member AB. And the same thing goes for this UDL and these support reactions. And we will need this angle here, theta, in our calculation. So let's calculate it. Tan theta is equal to perpendicular upon base. Perpendicular is 3 meter and base is 4 meter. And if you calculate theta from here, it's equal to 36.87. And also this angle here is equal to 36.87. And the reason is that when you have two lines intersected by one single line and there is a Z pattern being formed here, the alternate angles in this Z are equal. So if this is theta 1, this is also going to be theta 1. Similarly, this pair of adjacent angle is also equal. Furthermore, let's assume two pair of perpendicular line intersecting each other. And now let's assume another pair of perpendicular lines that are intersecting each other but are rotated at an angle of 36.87 in counterclockwise direction from these lines. And these are rotated at an angle of 36.87. If this is 36.87, this is also going to be 36.87. And this angle here is also going to be equal to 36.87. And this one as well. So let's apply this concept at A point. Assume an imaginary line here. And if this is theta equals 36.87, this angle is also going to be equal to theta. Similarly, this angle here is also going to be equal to theta. And in the last, at A point, this angle is also going to be equal to theta. Now let's start resolving the forces into their components at A point. So this component here is equal to 5.357 cos theta. Since this component has an angle theta adjacent to the resultant force, that is 5.357, it's going to involve the term of cos theta. And this component here will be equal to 5.357 sin theta. And note that theta here is equal to 36.87 degree. Similarly, this component here is equal to 15 cos theta. And this component here will be 15 sin theta. And after resolving the forces into their components, let's calculate the net internal force at A point. One thing I forgot to add here is that the local axis for the member AB is as follows. We have x-axis along the length of the member and y-axis perpendicular to the length of the member. And after resolving forces into their respective components, we need to calculate the net forces along these local axes. So let's do that. So along x-axis we have 15 cos theta and 5.357 sin theta. So let's calculate the net force. 15 cos theta. Let's assume that left force is positive and right force, the force going towards the right, is negative. So this is equal to 5.357 sin theta, and 15 theta is equal to 36.87. and is equal to 8.785. And since it's positive, it will be in the direction of this component. So net force will be in this direction. Now what about y direction? We have two forces, 15 sine theta and 5.35 cos theta. So 15 sine theta, and let's assume that the forces which are going upward are positive. 15 sine theta plus 5.357 cos theta, and theta here is equal to 36.87. And if we calculate it, now remove all of these forces and apply these calculated net forces at a point, which are along the length of the member and perpendicular to the length of the member. We have 13.280 acting in y direction, 13.280, and in x direction, local x direction, we have 8.785. Now we need to resolve this UDL into components which are parallel to this member AB and perpendicular to this member AB. So let's do that. So we have this resultant force acting here at a distance of 1.5 meter, and this is going to be 15 cos theta, and this force here will be 15 sine theta. 15 sine theta would be equal, and theta here is equal to 36.87. 15 sine theta is equal to 9 kilonewton, and 15 cos theta is equal to almost equal to 12 kilonewton. After calculating the components of the resultant force that is coming from UDL, we just need to divide these components by the length of the member, and let's assume the length of this member as equal to L, and this angle here, since the Z pattern is forming here, is equal to 36.87 as well. And L from here, this is going to be perpendicular and this is going to be base, and if I use Pythagoras theorem, L square is equal to perpendicular square plus base square. L from here can be calculated as Alright, so the component of UDL which is parallel to the member AB is equal to and is equal to 12 kilonewton divided by the length of the member. This force needs to be distributed along this length of the member. 12 divided by 5, which is equal to, and similarly we can calculate the UDL perpendicular to member AB by dividing this force by the length of the member. So the UDL which is parallel to the member AB is equal to 2.4. So let's draw that. And the UDL which is perpendicular is equal to 1.8 kilonewton per meter. And at the last we have to resolve this force 5.357 into the respective components. We know that this angle here is equal to theta, which is equal to 36.87, and using the same concept that we applied at A point, this angle here is going to be equal to theta, and since this component has an angle adjacent to the resultant force, this is going to be 5.357 cos theta, and this will be 5.357 sin theta. This is equal to 3.21, and this is equal to 4.285. And after resolving all of the forces into their respective components along the local axis of the member, we are in a position to write shear force, bending moment and axial equations, and then plot those diagrams for this member, for this inclined member. So let's do that. Now before writing shear force, bending moment and axial equation, first we need to discuss sign convention. So let's say we have a member which is part of the structure, and we will be using method of section, that is we will cut different section along the length of the member to write shear force, bending moment and axial equations. So if I take the coordinate from the left hand point or left hand side of the member, then in this case upward shear force will be positive and clockwise moment will be positive and leftward force will be positive, axial force. So if I'm moving from left to right, that is I'm taking coordinate from this side of the member, then in this case these will be the positive sign conventions for shear force, bending moment and axial force. And on the other hand, if I have a member and I cut a section and take a coordinate from this end of the member, then in this case, that is if I'm moving from right to left, in this case downward shear force will be positive, counterclockwise moment will be positive and rightward force, axial force will be positive. So it's entirely up to you from which end you take the coordinate from. You can take it from the left hand side or the right hand side, it doesn't matter. They will give you the same shear force, bending moment and axial diagram. And for this question I'm going to take the coordinate from the left hand side, that is I'm going to move from left to right, and I will be using these sign conventions, that is upward shear force will be positive, clockwise moment will be positive and axial force, which is towards the left, will be positive. And as I mentioned earlier, we will be using method of section to write equations, and in this case we need only one section, that's it, because we have a UDL acting along the length of the member as well as perpendicular to the length of the member, and we don't have any kind of discontinuity between A and B point in the loading. So we need to take the coordinate from the left hand side and let's call it as X. For writing shear force equation, stand on the section, C on the left hand side, take the algebraic sum of all the vertical forces that are acting on the member. So we have 13.280 which is vertical, and since I mentioned that upward force will be positive, and since according to local axis of the member this force is going upward, so it's going to be positive 13.280 positive. And we have another force which is shown by purple color, and it's acting downward, and we are talking about this UDL here, and this UDL has a resultant equal to this area, and this area is equal to 1.8 multiplied by X, and since it's acting downward it's going to be negative. And now to write moment equation, stand on the section, C on the left hand side, take the algebraic sum of all the moments that are acting on the left hand side of the section on the member. So we have this 13.280 acting in clockwise direction about this section, and it has a perpendicular arm of X. So 13.280 into X minus this load 1.8x, which is due to this UDL, and it has a distance of, it is acting at a distance of x by 2 from this section. So we have 1.8x creating a moment of 1.8x multiplied by x by 2. X by 2 is the perpendicular arm of this force 1.8x with respect to this section. And if we simplify it, now to write axial equation, stand on the section, C on the left hand side, take the algebraic sum of all the horizontal forces. We have this 8.785 which is acting towards the left, and according to sign convention left force is positive, so it's going to be positive. and we have this UDL indicated by sky blue color, and its intensity is equal to 2.4 kilonewton per meter, and the resultant horizontal UDL acting before this section is equal to 2.4 into x, and since it's going towards the right, it's going to be negative. Alright, now we are in a position to draw the corresponding diagrams. So let's first start with the shear force diagram. So this is the 0, 0 line, and we have x here, and along the y-axis we have shear force ordinate. And previously we calculated the length of this inclined member, and it was coming out to be equal to 5 meter. To write shear force equation, substitute different values of x here along the length of the member. So first I'm going to substitute x equals to 0, x equals to 0 in this equation, and this gives me, and the next value that I want to calculate the shear force on is equal to 1, x equals to 1, and shear force at x equals to 1 is equal to. Now it's entirely up to you what difference of interval do you take. In this case I'm going to take 1 meter interval difference between the calculated shear force. So the next x value that I'm going to calculate shear force would be equal to 2, and then 3, 4 and 5. So the highest value of shear force is equal to 13.80. First mark up the axes. Let's take 15 here, and 1 will be here. So at x equals to 0, v is equal to 13.280, which would be somewhere here, and at x equals to 1, v is equal to 11.480. At 1, 11.480 would be here, and at x equals to 2, v is equal to 9.68. Since in this equation the highest power of x is equal to 1, this equation represents a straight line. So this diagram, the shear force diagram for this member, would be represented by a straight line. Similarly, to plot bending moment diagram, substitute different values of x in this equation along the length of this member. So x starts from here, and on the y-axis we have the ordinate bending moment. So I'm going to substitute x equals to 0 to 5 with an interval of 1 meter. And the unit of the bending moment for this question is equal to kilonewton dash meter. The highest value of moment is equal to 43.5, and according to this let's take 50 here, somewhere here. So it means that 25 will be here. And at x equals 0, m is equal to 0. And at x equals 1, m is equal to 12.38. At x equals 2, m is equal to 22.96. The highest power of x in this equation is equal to, which means that it represents a second degree curve or a parabola. To get the diagram, plot through the points. And this moment here is not equal to 43.5, it's equal to 43.9. So this here is equal to 43.9, and there should be a moment here. Yes, at this end of the member, the moment acting is equal to 43.9. 43.9. And now, using the same concept, let's draw the axial diagram for this member. As we did in the previous case, I'm going to substitute different values of x in this equation, calculate the value of axial force at 0 to 5 with an interval of 1 meter. So at x equals to 0, 1, 2, 3, 4, and 5. So the highest value of axial force occurs at x equals 0, and it's equal to 8.75. And let's mark the axis of axial force according to this value here. So let's say that 10 is somewhere here and 5 is somewhere here. And at x equals to 5 is equal to 3.215. This value should be negative. And 3.25 should be somewhere here. And this equation, the highest power of value in this equation is equal to 1, which means that this equation represents a straight line. And if we connect these points, draw through these points, this should be a straight line. And this is our axial diagram. This portion is positive and this is the negative. To write equations, we need to cut section in this member BC. So the first section would be drawn here, section 1,1. Since the discontinuity in the loading after B point occurs at this point load, so we need to cut a section before it. And after this point load, the discontinuity or the change in loading occurs at this point, so we need to cut a section here. And the last section, section 3,3, would be in between this point load and this reaction. As in the previous case, I'm going to take the coordinate from the left hand side. To write shear force equation, stand on a section see on the left hand side, take the algebraic sum of all the vertical forces acting before this section. So we have this 5.357 acting upward, hence positive. To write a moment equation, stand on the section, see on the left hand side, take the algebraic sum of all the moments produced about this section. So moment is equal to 43.928. This is going to be positive since it's acting in clockwise direction, and this force is also creating a clockwise moment about this section. So this is also going to be positive 5.357, and it has a perpendicular arm of x1. A, which is the axial equation, will be equal to 0 since we don't have any horizontal force acting along this member. One more thing I forgot to mention here is that section 1-1 ranges from 0 to 1 meter. That is, it will help you draw the diagrams from 0 to 1 meter in this portion. And similarly, section 2-2 will help you draw the diagrams from 1 meter to 2 meter. And the shear force in this case for section 2-2 is equal to, we have this vertical force 5.357 acting upward. This will be positive, and we have this 20 kilonewton force going downward, and this gives us minus 17.643. And moment equation for section 2-2 is equal to, we have this 5.357 with a perpendicular arm with respect to section 2-2 equals to x2. So this will produce positive moment 5.357 x2, and we have this moment acting before the section plus 43.928, and we have this 20 kilonewton force, and it has a perpendicular arm with respect this section 2-2 equals to x2 minus 1 meter, and this force is creating counterclockwise moment about this point. So this is going to be negative 20, and perpendicular arm is x2 minus 1. And the section 3-3 ranges from, it starts from 2 meter and ends at 3 meter. And using the same principle, stand on the section, see on the left hand side, take the algebraic sum of all the vertical forces. We have this 5.357 again, 5.357 going upward, hence positive, and we have this 20 kilonewton force going downward along with this 20 kilonewton force, which is also going downward, hence negative. And shear force in this case is equal to minus 34.643, and moment for this section is 43.928 positive, and we have this 5.357 which has a perpendicular arm of x3 with respect to section 3-3. This will be positive since it's creating a clockwise moment about this section. And we have this 20 kilonewton force creating counterclockwise moment, and it has a perpendicular arm of x3 minus 1 with respect to section 3-3. So minus 20 into x3 minus 1, and this 20 kilonewton force has a perpendicular arm of x3 minus this distance 2 meter, x3 minus 2. Alright, after doing this, let's calculate the values of moment and shear at different points along the length of this member using these equations. So let's start with section 1.1. So we'll draw shear force here, moment diagram for this member here, and axial diagram here. So let's mark up the axes. Let's take 20 here and 40 here. And at x equals 0, shear force is equal to 5.357, which will be around somewhere here. And at x equals to 0.5, it's constant. 1, it's also 5.357. So at x equals to 0, m is equal to 43.928. 43.928 will be somewhere here. And what about axial force? It's equal to 0, and it will overlap this 0, 0 line. Now let's draw the diagram in between 1 meter and 2 meter, that is this segment. And for moment values, now again using the same principle, draw the diagrams for this segment here from 2 meter to 3 meter.